Hey, this is part two. We're continuing from the book Prevent and Reverse Parkinson's Disease and Chronic Fatigue Syndrome by me, Pete Rogers. We're talking about diabetes, insulin resistance, what causes it. So here's the most important thing you can know about diabetes is that dietary fat can just get across the plasma membrane of the skeletal muscle cell. It doesn't need a plasma membrane protein transporter. It's what's called the flip-flop maneuver. It can intercalate itself into the outer leaflet of the plasma membrane and then flip-flop into the inner leaflet of the plasma membrane and then diffuse into the cytoplasm. So it can become protonated to facilitate intercalation. But once it gets into the cell, it can then get into the mitochondria. And this is sort of a bulk flow effect whereby it gets into the skeletal muscle cell in proportion to the amount of fat in the blood. So the more fat you eat, the more fat gets into the skeletal muscle, the more likely you're going to become diabetic, have increased insulin resistance. So the only way to prevent this is don't eat so much fat. And that's why I always tell you, you want to minimize your dietary fat. The masters of diabetes guys like Bobby Bittero and Cyrus Kumbada, they're going to tell you keep your dietary fat below 15% of your total calories. I would recommend keep it below 10% of your total calories. Okay, when Kempner had his people on the white rice diet, he was getting it down really low, like around 3% of calories. So, McDougall would say on average his was about 7% of calories from fat. Esselstyn say he just wants it below 10%. He didn't specify because, depending on the exact diet, it'll be kind of variable. The things that are lowest in dietary fat, white rice has 1% of calories from fat. Potatoes and sweet potatoes have 1% of calories from fat. The lowest fat bean is lentils. They have 3% of calories from fat. Black beans are about 4% of calories from fat. Fruits tend to be very low in fat too, usually in the ballpark of 1 to 4% of calories from fat. So those are all great foods for preventing diabetes. Okay. But that's the point I'm making is you can't win the diabetes game eating fat. And some people say, well, I heard about a paleo keto carnivore who had a reasonably good blood glucose level. Well, the problem with them is if you feed them any carbohydrates, they'll fail their oral glucose tolerance test. They have a lot of insulin resistance, and that's a very atherogenic diet. It's a very unhealthy diet. You can kind of fake it, but you're not going to make it with that long term, okay? All right, so who figured out that high-fat diets cause diabetes? And that was figured out a long time ago, like the J. Shirley Sweeney paper back in 1927 from the Archives of Internal Medicine. And then in the 1930s and 1970s, a whole bunch of other people confirmed those findings that high-fat diets cause insulin resistance and elevated blood sugars consistent with diabetes, including Rabinowitz, Himsworth, Kempner, Pritikin, McDougall. These guys all did great work, but the greatest paper ever written in the history of diabetes research was the paper written by Michael Brownlee. Michael Brownlee is this guy, he's a genius from America. He had type 1 diabetes, and he had read somewhere that type 1 diabetics are probably going to die in their 30s, and he was frightened by that. So he decided to devote his entire life to researching diabetes, and he figured it out. He won the Banting Award as Best Diabetes Researcher in the World in 2004, and his paper is called The Pathobiology of Diabetic Complications, a Unifying Mechanism. And this paper is so good. It's like the Sistine Chapel of medical research papers. One of the greatest medical research papers in any field ever written. It's like, I cried when I read it. It was so beautiful. It was so perfect. It was his legacy, his life's work to show, how insulin resistance occurs by overwhelming the inner mitochondrial membrane with excessive numbers of electron transporters. Okay, then the gradient goes too high, and you can no longer pump electrons into the intermembranous space, and it starts going backwards. Okay, it's in the Diabetes Journal in June of 2005. You can get a free copy of it. If you go online, you can get a free copy of it. It used to be you could go to the ADA and even give your email, and they'd let you watch the video for free, but you might not be able to do that anymore. So Brownlee showed that an excessive amount of dietary fat leads to an excessive electrons getting pumped into the intermembranous space too rapidly, and it starts going backwards. Okay, once it starts going backwards, it'll drop electrons down into the mitochondrial matrix. Some of those will combine with oxygen to make superoxides, and normally those can be neutralized by superoxide dismutase, but if there's an excessive number of them, then sometimes progressive free radical reactions will occur. If you got free iron in there, you can get the Fenton reaction happening. You can produce hydroxyl radicals and have all kinds of problems. We'll get to that later, okay? But sat fat in particular is the worst one. Sat fat comes especially from eating animal foods. But the other fats will eventually lead to that effect as well. They all increase your risk of obesity and eventually lead to increased risk of diabetes. Okay, here is showing some of the reactions that can happen. If you get an excessive amount of free radicals from an excessive amount of electrons being dropped into the matrix, normally a few electrons are always dropped into the matrix, but when the number becomes excessive, you can end up having the superoxides and the related free radical reactions damage some of the DNA in the mitochondria, and then it activates a DNA repair enzyme called PARRP. And that will then trigger a cascade of reactions that will actually damage an enzyme in glycolysis called glyceraldehyde 3-phosphate dehydrogenase. Okay, we're not going to go through the whole pathway because it's a bit long, but if you read his paper, he'll go through all the details of it. Okay, I just want you to see what happens because this is sort of unleashing the dogs of war. It sets in effect multiple secondary harmful reactions. So this is the enzyme in glycolysis, glyceraldehyde 3-phosphate and 3-phosphate dehydrogenase. And when you inhibit that, the glyceraldehyde 3-phosphate substrate then runs through side reactions, including the PKC pathway, protein kinase C pathway, and then that will lead to production of diacylglycerides and all kinds of bad things happen. Methylglyoxal, forms advanced glycation end products, does a lot of damage. Okay. This is sort of a quick look at some of the things that happen with elevation of MGO methylglyoxal as a side pathway coming off of the accumulated glyceraldehyde 3-phosphate because the enzyme glyceraldehyde 3-phosphate dehydrogenase is blocked. Okay. And once it makes advanced glycation end products, you can glycate things inside of the cell, proteins inside of the cell. You can glycate proteins in the extracellular matrix, damage the collagen. You can glycate proteins in the blood like albumin. You can glycate your hemoglobin like hemoglobin A1C. Okay, and this can activate other inflammatory pathways by binding with, macrophage mesangial cells in the kidney, for example. You can damage your collagen, like you can damage your collagen in your spine, and this can contribute to spinal degeneration, like DISH, diffuse idiopathic skeletal hyperostosis, because weakening of the ligaments can contribute to leading to segmental instability between the vertebral bodies and the intervening disc space. And then the spine will fix itself by growing bone spurs to fuse across the vertebral body levels, across the disc space. And that will lead to back pain, back stiffness, and weakness. Okay. So what I'm trying to say is, once you unleash these dogs of war, they start damaging things all over the body. And this is one of the obvious reasons why a low-fat diet is better, because you don't want this stuff to happen. This is just a little bit more detail on an advanced glycation end product reaction. Okay, it'll bind to the side chain of protein with a nitrogen residue sticking out, and then this will become an irreversible reaction to damage the protein. So it's called an advanced glycation end product, AGE. Okay. Here's showing the hemoglobin A1C glycation. Typical red blood cell lasts about 120 days. So the measurement of hemoglobin A1C, glycated hemoglobin inside of red blood cells, they last about 120 days. So the hemoglobin A1C is an estimate of the overall glycemic control. So normally you want your A1C less than 5.5. 5.5 to 6.5 is pre-diabetes. 6.5 and over for your hemoglobin A1C is, full-blown diabetes. And the higher it gets, the more uncontrolled the diabetes is. Okay, this is just showing some of the secondary pathways that will come off the activation of the protein kinase C pathway. And it's going to include all kinds of bad things. It's going to have prothrombotic things, like you're going to inhibit nitric oxide synthase, so you won't make as much nitric oxide. Nitric oxide prevented platelet aggregation, so now you're going to lose that benefit, meaning that your platelets will become more activated, more prone to clotting. What is a clot? Atherosclerosis is a clot inside an artery, so you become more prothrombotic. You become more atherogenic. Diabetes is intrinsically atherogenic, okay? Also, by inhibiting nitric oxide production, you're going to have more vasoconstriction, so that's going to predispose you to high blood pressure. So usually patients with diabetes also have high blood pressure. It makes sense from looking at these mechanisms, okay? They'll also decrease their ability to dissolve blood clots in the arteries. Decreased fibrinolysis is the fancy way of saying that, which means they're more prothrombotic, more atherogenic. And this will occur in small vessels. They sometimes call it a microvasculopathy. And basically, when you damage these small arteries of the foot down in the toes, you're kind of screwed because there's no outflow, meaning that they're too small to place a stent. They're too small to place a surgical bypass graft. So once these arteries fully occlude, the patient will typically need an amputation. It's very common for patients with advanced, poorly controlled diabetes to get amputations. I can tell you, not a day goes by that I don't see some diabetes amputations. Every major hospital in the Western world is chopping off lots of toes. You know, you chop off the toes first, then you do the midfoot, and then you often go to, there's different types of amputations, but you'll often go to a below-knee amputation at that point. And if it keeps progressing, you know, an above-the-knee amputation, it's bad. Diabetics have terrible peripheral vascular disease. Okay, there's all these side pathways of inflammation. We're not going to go into all that, but the bottom line is you really want to prevent it. Okay, so that'll be the end of part 2. And then in part 3, I'll go through the specific causes one by one. There's going to be a lot of them. Things that increase insulin resistance, so that if somebody were to have diabetes, they could learn about all these things and then try to avoid them all. That's how you cure a disease, by avoiding the things that cause it. So anyways, I hope you found that helpful.